Hi, this is Kevin. Welcome to part two of my lecture on chapter 8 of the Zelle 3rd edition Python book. And the first part of the chapter was about loops, in particular about the while. And the second part of the chapter um, really focuses on Booleans and maybe the impact that using Booleans in a particular way has on programming in general and on loops in particular. Okay, so so far we've worked with the if and the while, and they both use Boolean expressions. As you recall, these expressions evaluate to either true or false. Okay, and these are not strings, true or false. They are the actual keywords, capital TRUE and capital FALSE. So far we've used Boolean expressions to compare two values. Okay, so for instance, we have a while here, and we say while x is greater than or equal to 0. Okay, two values, one operator, right? Okay, let's get a little bit more crazy here. Okay, sometimes our simple expressions do not seem expressive enough. Expressive enough to model the conditions in the real world that we're trying to emulate. Suppose you need to determine whether two points are in the same position. So now we go back to geometry again. Their x coordinates are equal and their y coordinates are equal. Okay. I apologize for the geometry, but that's what we're going to do. So here's some code that might test that. We say, apparently we get the x coordinates from these objects, one represented by the variable p1 being 0.1 and the other by the variable p2. So if we get their x, the coordinates with get x, so we say if get x of p1 is equal to get x of p2, then if the get y of p1 is equal to the get y of p2, then the points are the same, else the points are different, else the points are different. Okay, so here we've only got two dimensions on each object that we're trying to compare, and doing this with ifs and elses is already pretty awkward, right? So let's check out three Boolean operators, and, or, and not. Those are going to help us express this in a less awkward way. So the Boolean operators and or are used to combine two Boolean expressions and produce a Boolean result. Okay, so we would form these by having the expression on the left and expression on the right, or the expression on the left or expression on the right, and or. So what we're going to see here is called a truth table, and this may be the first time you've seen them. It's not the first time for me because I was a philosophy major in college and I took, I think, a couple of courses in symbolic logic, and logicians use these kind of tables all the time. Okay, so we'll talk you through it here. So the end of two Boolean expressions is true exactly when both of the expressions are true. We can represent this in a truth table. So this thing is called a truth table. So up in the headings we have the first expression we're calling P, the second expression we're calling Q, and P and Q is the combination of the two using the and. Why do we use P and Q? Logicians have always had a tendency to use the letters of this part of the alphabet, and so these kinds of examples often use P and Q, but to new people that can be kind of off-putting, but they're arbitrary. So what we can see here's how we read the truth table. If a P is true, that's because it has a T, and Q is true because it has a T. Well, P and Q is also true, it has a T. Every other combination for P and Q leads to an F for false. So if P is true and Q is false, then P and Q is false. The opposite, PQ, is false. And if they're both false, then false. Okay? So we go back to the claim in the top of the slide. The end of two expressions is true exactly when both of the expressions are true. Okay? And if you look at the truth table, you can see why that claim is accurate. And now they're talking you through the table. I think I did a better job. Okay, well, what about or? What if we did a truth table for P or Q? Okay, so again, we have a column for P, a column for Q, a column for P or Q, and we typically put these things in the same order every time. So row 1 is usually true, true. Row 2, true, false. Row 3, false, true. Row 4, false, false. Why? There's a tradition of that's how we organize a truth table. Could you mix those up? Yeah, you could, but you wouldn't be one of the club, right? Okay, so what's the claim they make up here? The or of two expressions is true when either expression is true. Okay, so this is interesting. We have 3 situations in which it's true and only 1 situation in which P or Q is false. So when they're both true, it's true. When P is true and Q is false, it's true. When P is false and Q is true, it's true. The only situation in which it's false is when both P and Q are false. Okay. Note that this isn't the way that we use the word or in everyday English language. Okay. So let's go back and look at that slide. Okay. So this kind of or, this kind of logical or, is often described as the inclusive or. And the way that we use or in conversational English is typically described as the exclusive or. Okay, so I'll give you an example of an exclusive or. Let's say that there's a department. Mary is the head of the department, and I work for her, Kevin, right? And the company's going to have a company picnic. And the company picnic is a benefit for the employees, but it's a chance for the employees to show their loyalty as well. So every department is expected to have at least 1 people at the picnic, right? So the big boss comes into the office and they say, will you be at the picnic? And Mary looks at me, and then I nod, and then she says, either I will be at the picnic or Kevin will. And then the big boss says, that's fine. You'll have somebody to represent you. So comes the day of the picnic, say it's Saturday afternoon, and we both arrive at the picnic, okay? Now, in the common sense of or as exclusive, people would be surprised because they would expect Mary to be there or Kevin to be there, but not both, okay? Um, so that's the exclusive or, okay? In the inclusive sense of or, nobody would be surprised because uh, it's true when P and Q are both true. Okay, so this is different from the way we use or in everyday English, and it's a very helpful construct in programming logic, the inclusive or. You won't be surprised to know that there's a not operator in Python. It's just not, and you can apply it to an expression. Okay, so the not operator computes the opposite of a Boolean expression. Not is a unary operator, meaning it operates on a single expression. So we only have P because there's only a single expression. So we have P and not P. So if P is true, not P is false. If P is false, not P is true. So you just get the opposite with not. Okay. We can put these operators together to make arbitrarily complex Boolean expressions. And there's an art to this, and we're going to talk about it a bit. The interpretation of the expressions that we build relies on the rules for the precedence of operators in Booleans. Now, the author claims this. I just want to point out that I've been telling you with math expressions all along to include all the parens such that what we mean to say is unambiguous and the reader doesn't have to remember the rules of precedence of operators in math. Okay, well, this is true for logic as well. Okay, so even though one could rely on the rules of precedence, and we'll tell you what they are in a second, um, don't. Okay, always include enough parens so that what your expression says is obvious on its face. So here's an expression where that was not done. A or not B and C. How should this be evaluated? The order of precedence from high to low is not, then and, then or. That statement is equivalent to A or not B and C. Okay, and that's pretty complex. That's hard for me to get my head around. So if you wanted an expression that said that, definitely don't put in the text that you see in bullet 1 because you may not even understand it when you come back to it. Since most people don't memorize the Boolean precedence rules, use parentheses to prevent confusion. Very good advice. Okay, so now we're going to get back to this example of finding out if 2 points are in the exact same place. Okay, and again, on a Cartesian plane, there's an x-axis and a y-axis, and so you can locate any particular point by the combination of its x and y coordinate. And to tell if 2 points are located at the same place, they have to have the same x coordinate and the same y coordinate. Okay, so now here's what we can say. If the x coordinate of P1 is equal to the x coordinate of P2, and the y coordinate of P2 is equal to the y coordinate of P1, then the points are the same, else the points are different. Now, I want to tell you that I am really a stickler for readable code. So if I tested P1 to P2 in the first part of this compound expression, I would have put them in the same order in the second part. So this swapping them around is, I think, bad form. The entire condition will only be true when both of the simpler conditions are true. Okay, well, that makes sense. Okay, so we'll see when we get to chapter 9 that our author thinks that a good kind of a complex thing for us to do is to write a simulation of a racquetball game. So this is foreshadowing some programming that's coming up in the next chapter. So say you're writing a racquetball simulation, which we do in chapter 9. The game is over as soon as either player has scored 15 points. How can you represent that in a Boolean expression? Okay, so in that program, he has 2 players. He calls them A and B, and the score for A is called score A, and the score for B is called score B. And I just want to point out that these are not properly formed Python variable names, but we're going to excuse that because that's not the point we're trying to make here. So we say if score A equal 15 or score B equal 15, then the game is over. When either of the conditions becomes true, the entire expression is true. If neither condition is true, the expression is false. Okay, and that's going to be helpful when we get to read the programs in chapter 9. Okay, so let's say we want to construct a loop that continues as long as the game is not over, which we do in chapter 9. You can do this by taking the negation of the game over condition as your loop condition. Now, this is an interesting point, okay, because if we're going to have the game in a while, right, well, then we're going to want to do it while the game is not over. So here's what he's done here. He's just said while not as a unary operator. If we wanted to apply to this whole compound expression, well, we're going to have to put that expression into parens. So we say while not, score A equal 15 or score B equal 15. And then continue playing. So this would be the code for our simulation. And again, when we get to chapter 9, we're giving you a sneak preview of what we're going to see in chapter 9. Or maybe it's a little more complex. He says some racquetball players also use a shutout condition to end the game, where if one player has scored 7 points and the other person hasn't scored yet, the game is over. Okay, so what's he saying here? So he wants to say, while not, some combination of the winning conditions. Okay, so he says, while score A, while not, and then one way to win, score A equal 15. Another way to win, score B equal 15. Another way to win, score A equal 7 and score B equal 0. Or another way to win, score B equal 7 and score A equal 0. Okay, and notice this was so long that he had used a line continuation characters to carry the expression over onto multiple lines. And he's kind of lined up these expressions, and this is considered good code formatting. Okay, so this is a bit hard to read, but it does the job. Okay, so let's look at another game that we might want to simulate that we don't talk about, I think, in Chapter 9, volleyball. Okay, because volleyball scoring is a little more complex. Uh, to win in volleyball, a team needs to win by at least 2 points. Okay, so in volleyball, a team wins at 15 points. If the score is 15-14, though, play continues just as it does for 21-20. Okay, so here's what we're going to wait. So one way to express this is this next bullet. So the score for A is greater than or equal to 15, and the score for A minus the score for B is greater than or equal to 2. So we've gotten to 15 and we're ahead by at least 2. Or the opposite. B has gotten to 15 and B is ahead by 2. Or the last of the bullets, this is simplified. Okay. So there's a built-in function called abs, which gives you the absolute value, right? Which gets rid of negatives, right? So here's what we do. We say if A has the score greater than equal to 15, or B has the score greater than equal to 15, and the absolute value of the difference between the scores is greater than or equal to 2, then we're done. Okay, now one of the interesting things here, and the point that the author is trying to make, and I think it's an excellent point, is sometimes, okay, it's very difficult to express when the game's over. Okay, so that's pretty challenging for how to write the expression at the top of the while loop. And what's going to come next are some ways of simplifying these complex Boolean expressions that will help you to have an expression at the top of the while that you find easy to read, and then other people will find easy to read when they come to maintain your code. So that's where we're headed. So the ability to formulate, manipulate, and reason with Boolean expressions is an important skill. Boolean expressions obey certain algebraic laws called Boolean logic or Boolean algebra. Okay, and these are the kind of things that they teach you in a symbolic logic course, or sometimes called just a logic course. Okay, so he's got some things here where he talks about here's how some operators work in algebra, and here's a corollary in this Boolean algebra. Okay, now if you already know how these things work in algebra, okay, well, this is really helpful. Okay, if you don't get hung up on this, right? This is a point that's made. This is kind of a course that was written for math majors or people who really dig math. All right. If you do, then this part of the slide is going to be helpful. If you don't, this is maybe going to lead you astray and waste your attention. Okay. So I'm going to focus on the right side. Okay. We can combine things. Okay. And they have, how can say this, they have predictable results. So if we have some Boolean value A that's either true or false, and that's either just, well, it could be the word uh, uh, true, or it could be the word false, or it could be a variable that has a Boolean value, or it could be an expression that when you evaluate, you get a Boolean value. Okay, so that combined with false, A and false is always going to be equal to false. Why is that? Well, because for an and to be true, they both have to be true. Okay, so if the right side is false, we know that it doesn't matter what the left side is. Okay. Uh, uh, if we have A and true, I'm sorry, I think I jumped. If we have A and true, that's going to be equal to A. So that's going to be true if A is true and false if A is false. And if we have A or false, it's always going to be equal to A because an OR is going to be equal if A is true or B is true. But it turns out that the second one is always false, so we're counting on A. So whatever A is, that's the answer that we're going to get. Okay, and this level of thinking about Booleans and symbolic logic is useful, okay? And some people will take advantage of it in their code, okay? For some new people, this kind of thinking is taxing at first, okay? You probably wouldn't want to write code like this, okay, because it maybe be too taxing and you could maybe, spell out the expressions more explicitly and not use these, what I would call combination tricks, okay? But I teach this here because maybe you're trying to maintain some code in which a programmer has used one of these combinations because they sort of understand these shortcuts, right? And then you've got to figure it out. Okay? So, in Boolean algebra, or this, kind of Boolean reasoning, anything that's ORed with true is going to be true because only one of them has to be true. Both and OR distribute. So if we say we have A or B and C, okay, we can turn that into A or B and A or C. If we have A and B or C, we can turn that into A and B or A and C. Now, if that makes a lot of sense to you, well, great. If you're not following it, maybe this is a mechanical transformation that you might go back to if you're thinking that you could use it. Okay, why would you want to do this kind of transformation? You'd want to do this kind of transformation because you have an expression at the top of your while loop and it's hard to read and hard to understand. And so you're trying to transform it into an equivalent expression that's easier to understand. Okay, that's the only reason that you would do it. If you already have an expression at the top of your while that, and this also applies to, the if from chapter 7, right? If the expression is already very readable, well then no reason to start transforming your expression in order to make it more readable. You're already done. Double negatives cancel out. And this, I don't know if we do this all over the world, but in the US, this is a thing that even small children understand. And they'll say something like, A double negative is equal to a positive. Okay, this is the kind of thing when you start calling each other names. Okay, so this is, I think, common knowledge, and maybe children say this all over the world. Okay, so if you have a not A and you not it, well, uh, the answer is equivalent to A. So this is a simplification. Okay. Now, the very last one turns out to be pretty powerful, and it's probably the least intuitive of all of them. And these two transformations, they're called De Morgan's laws, and De Morgan, I guess, was a logician of a long time ago, and told the logic world that these transformations were always going to work. So if you have a not A or B, you can transform it to a not A and a not B. See how that flops? Okay. If you have a not A and B, you can transform it to a not A or a not B. Okay. So these things are all ways to transform the expression that you have into an expression that you find more readable, one that you prefer. If you already have an expression that you love, you don't need to start the transformations. Okay? So your motivation for transformation is you don't like the readability of the expression that you start with. Okay? And in a way, uh, these are classic refactorings, right? We start with an expression that works that maybe is not readable, right? And we try some series of refactorings, and ideally what we're looking for is a more readable expression, but the behavior would be exactly the same. It's classic refactoring. So we say that we can use these rules to simplify Boolean expressions. So here we're saying while not score A equal 15 or score B equal 15, we can change that through the application of one of those De Morgan's laws to while not score equal 15 and not score B equal 15. Okay? And maybe that's easier to understand. We want to continue with our simulation when A hasn't won and B hasn't won. Okay? Which is what this expression up here says, but not so intuitively. Okay? Again, if we like the expression up here, on bullet 2, we're done. Okay? These are refactorings. They're supposed to make things more readable, more maintainable, more testable. Um, if if you like where you are before the refactoring starts, well, you don't do the refactoring. Um, so this becomes while score A not equal 15 and score B not equal 15. Okay, so the not equal again is a combination of the exclamation point, which we call the bang, and the equal sign. Isn't this easier to understand? Yeah, I think it is for me. You be the judge for you. Okay. Like any other refactoring, you're going to keep refactoring your code until you believe that it's in the best condition to leave it. Okay. Sometimes it's easier to figure out when a loop should stop rather than a loop should continue. In this case, write the loop at termination condition. That's when it should stop, and put a not in front of it. After a couple of applications of De Morgan's law, you're ready to go with a simpler but equivalent expression. Again, refactoring in its classic form. Okay, so let's talk about some more things related to Booleans and such. The if and while can be used to express every conceivable algorithm. Okay. For certain problems, an alternative structure can be convenient. So we're going to talk about a structure that they have in certain other programming languages that the mothers and fathers of Python decided we didn't need. You know, just like my mom used to say, I used to tell my mom, "Oh, mom, you know, let's get the big chocolate cake at the grocery store." She would say, "Oh, Kevin, we don't need that." Well, the mothers and fathers of Python have taken a page out of my mom's book. So the structure that they said we didn't need, um, we'll see in a second, is called an until. Uh, in this in the pseudocode that we're going to see in a couple of slides, we say repeat until, okay, and then there's a condition. There's the equivalent of this in the Java language. There the equivalent of this in a couple other languages. Um, if you want to have this kind of logic in Python, you need to build it out of the parts that we do have. Okay. So let's go back. So the while is so the for in is a pretest loop. Okay. If there isn't anything in the structure that we're iterating over, then we don't do the body of the loop. Okay, that's why we know it's a pre-test. We can execute it 0 times. Okay, the while is a pre-test loop, right? So it's possible to execute the code block that's the body of the loop 0 times. There are times when you want to make sure that you execute the body of the loop at least 1 time. And that's with the post test loop. This is a structure that we don't officially have in Python. That's what that does. So what would be an example? Well, say we want to write a program that's supposed to get a non-negative number from the user. If the user types an incorrect input, let's say they gave us a negative, the program asks for another value. It reprompts. The process continues until a valid value is entered. This is some form of input validation. This is what I might call single facet input validation. Okay. In a prior chapter, I talk about multifaceted input validation. So in pseudocode, we've represented this with repeat until expression, and then whatever we want to do on the inside is indented in the code block. So this is pseudocode. Repeat, get a number from the user until number is greater than or equal to 0. Okay? And this is what this would look like in a programmer flowchart. Again, not because we want you to learn how to draw programmer flowcharts, because we find it's a good teaching tool, and this is a good way to draw this picture and say, this is a post-test or test after loop. We test after we do the body of the loop. That means it's going to be done at least 1 time. Okay, well, given that we don't have a statement to implement this directly in Python, how do we do it if we have this kind of use case that we want to implement? Well, when the condition test comes after the body of the loop, it's called a post-test loop. post-test loop always execute the body of the code at least once. Python doesn't have a built-in statement to do this, but we can do it with a slightly modified while loop. Okay, how? So we seed the loop condition, so we're guaranteed to execute the loop once. Okay, so like most programmer tricks, this is essentially cheating. Okay, we're forcing the program to have some kind of behavior. Okay, so the while loop says while number less than 0. Okay, and what we do is we seed the value of -1 into number. Okay, so that it passes the first time through. All right, and then we prompt the user enter a positive number, and then we assign it to number. We convert it to a float. Okay. Now this is going to go around until either we assign a positive value or it blows up because we typed HIMON, right? Because we don't have robust enough code to deal with non-number inputs. Some programmers prefer to simulate a post-test loop by using the Python's break statement. Okay, executing the break statement causes Python to immediately exit the enclosing loop. Break is sometimes used to exit what looks like an infinite loop. Okay. Okay, so we're going to say on a subsequent slide that break is controversial. Okay, some programmers believe in break, others don't. I personally am on the conservative side of this. I believe in using break only in very limited circumstances. There are perfectly good programmers who feel free to use it. Okay, you're going to form your own opinion and develop your own style. Okay, so what if you developed a style that included the use of the break statement? Okay, well, here's what would happen. We say while true. Now this is a bold trick. Okay, what does while true do? Well, it creates an infinite loop. Okay, so if in fact we didn't have a way to break out of the loop, while true would run forever because true is always true. Okay, I've always thought that that was exceptionally bold. So we prompt the user enter a positive number. Okay, and then this is interesting because then we say if x is greater than or equals 0. I think we meant to say if number is greater than or equal to 0, break. Okay, so he wants to exit the loop if number is invalid. Now, notice that he has an indented break on the next line. Okay, and he'll tell you that you can write code like this, but I'm going to tell you it's a bad practice. Okay, and I'll tell you when we're on the next slide. A while loop continues as long as the expression evaluates to true. Since true always evaluates to true, it looks like an infinite loop, which I said. When the value is non-negative, the break statement execute, which terminates the loop. And now we say, if the body of an if is only one line long, you can place it right after the colon. Don't do it, okay? The problem is that when people are reading the code, they gloss over it. They don't see it, okay? It's another line of text. Okay, the only thing that you're adding to your file that holds your code is one new line character. All right, so don't be putting a statement to the right of the colon on a one statement if. Indent it just like everything else. That's the better practice. Wouldn't it be nice if the program gave a warning when the input was invalid? Yeah, I agree. Let's look. In the while loop version, this is awkward. Okay, so let's see this. Uh, Number gets preloaded with -1 while the number is less than 0. We prompt for the number and we convert it with float. If the number is less than 0, uh, print the number you entered was not positive. Okay. We're doing the validity check in two places. Well, we're certainly repeating the code. Whether the top one is a validity check or just the controlled expression for the loop is another matter. Adding the warning to the break version only adds an else. So we say while true, then we prompt. If it's greater than or equal to 0, we break. That's it. Indent it. We have a lot of code blocks that are only a single line long. Okay. Uh, uh, Put them on their own line. Okay. Else we print the warning. Yeah, that works. Okay. Okay. Now, what comes next? Statistically, some programmers prefer the following approach. So, while true, we prompt for the number. If the x, again, I think he should have said number, it's greater than or equal to 0, break, print this. Here the loop exit is in the middle of the loop body. This is what we mean by a loop and a half. Now, this is a great textbook. I complain about some of the coding practices, but the computer science thinking, I think, is very strong, and it's the reason that we use it. Now, he talks about a loop and a half. I've never talked about a loop and a half in my entire 50-some years as a programmer. Well, 51. Okay. Maybe there are people who talk about a loop and a half, or perhaps he and his friends do, or he had a professor that talked about a loop and a half. I'm not sure you're going to find a lot of people who call this a loop and a half. Okay, but you can definitely do this. All right. The loop and a half is an elegant way to avoid the priming read in a sentinel loop. Okay, and here it is as pseudocode. While true, get next data item. If the item is the sentinel, break, indent that. See, he's afraid he's not going to get this on the slide, or process the item. Now, here's one of the problems that I have with break and the kind of code that comes along. Okay, break, does he turn this into real code? No, he doesn't turn this into real code. So you'll notice that there's no else. Okay, because the way break works is that we leave the loop, okay, and we don't come back. We go to the next, we begin to execute the Python statement that comes after the loop. That means that we jump over the rest of the code. Implied here is an else, okay, because this process the item, and this might be 1 line of code, or 2 lines of code, or 3 lines of code. There's an implied else here because the break jumps over them and right on out. Okay, so a lot of times with new programmers who are not used to seeing the break, it's not obvious to them that this is an implicit else. Okay, I'd rather see an explicit else. I would rather say if the item is the sentinel, next line, break, else, then we have the code block to process the item. Does that generate any more executable code? in the Python bytecode? Definitely not. Is it easier to read? It definitely is. Okay. Now, uh, so as you can see, is the item the sentinel we break? We jump past this, even though it's not hanging off of an else. Okay. Um, Again, I don't think that's the best code to write. It doesn't save any processing time, and it's tricky for beginners. So here's the question: are you going to use the break? That's the question. The use of break is mostly a matter of style and taste. And then he says, avoid using break often within loops because the logic of the loop is hard to follow when there are multiple exits. Okay, so I'll tell you why I use break very sparingly. Okay. Um, Way back when I got into programming, there was a movement called structured programming. Um, and this was based upon a theory put forth in the mid 1960s called um, structured programming theory. And pretty closely after that, in the 1970s, people adopted structured programming widely. Okay. And it had a lot of rules, and I think I've probably talked about some of them, but um, one of the rules was, or one of the rules that people added to it perhaps was every block of code, every code entity, which would include a function or an entire program, should have one entry point and one exit point. And typically, we enter at the top of a function and then we exit at the bottom. And this would be true for a loop as well. Okay, so when we break out of the loop, well then uh, potentially we have two exit points, and we do have an exit point that's not at the bottom. So if we go back here and we look at what we're doing, this while only has a single exit. It's just that it's in the middle. Okay. Well, most people think that's okay, a single exit. You definitely do not want to write some kind of a loop that has more than one break in it. You'll see them. You'll see people write nested loops that have breaks all over the place, and they're very hard to follow. They're very hard to test. They're hard to debug. So if you're going to use a break, and again, this is a stylistic choice for you, feel free to use it, but just use one, at most one, in a loop. Okay. And um, for me, having a loop, um, having a loop like this is the only way out. Okay. Uh, having a loop that has a condition on the while and a break, well, then that's got two ways out. Okay. And maybe that's okay, but is the number of ways that you exit a piece of code, uh, if you have one, you can understand it. If you have two, it might hurt your head. If you have three, I think you have chaos on your hands. Uh, which is why he says avoid using break often, I would say more than once within a loop, because the logic of the loop is hard to follow when there are multiple exits. Well said. Boolean expressions as decisions. So we talked about a little bit about this when we were covering chapter 7, so this won't be new. Um, Boolean expressions can be used as control structures themselves. Suppose you're writing a program that keeps going as long as the user enters a response that starts with Y, like our interactive loop. So one way you could do it, while the first character of the response is lowercase y or it's uppercase y. Okay? might have made more sense to shift it and only test one, but we're trying to talk about the Boolean rules. Be careful, you can't take shortcuts. So if you say while the first character of the response equal y or y, that's going to mean something else. Okay, and it's going to mean something else because you'll remember because of truth value syntax or truthiness. Okay, this string is always going to be true. Why? Well, because for a string, it's false if it's the empty string. It's true if it has any characters. Okay, so this is going to be true forever. So that's not what you want. All right. So be aware of truth value testing. And then we talk about truth value testing here. And as you can see, if we do a bool of an int 0, it's false, and int 1 is true, 32 is true, any non-zero int is true, any non-empty string is true, any empty string is false, any non-empty list is true, any empty list is false. Okay, we've covered this. Truth value testing, or truthiness. Okay, so the rest of the slides go with the end of the chapter where he's talking about a simple event loop. And this goes back to the things he was doing in chapter 4 and things that we don't do. So I'm going to stop here and encourage you to go on and play the Beyond the Textbook lecture for chapter 8. And I'm going to say goodbye until then. Bye-bye.